Ciao, Napoli. Ui, loud. Welcome to my speech on ZK 101. Hopefully this will get you started a bit on ZK. It's ZK 101. What is ZK and why should you care? First, a little bit about me. I'm Daniel Lumi. I'm a Web3 consultant and researcher specializing in ZK, L2s, privacy, and DAOs. We'll talk today about why should you care about ZK, what is a ZK proof, how do they actually work, and then applications for ZK. So why this talk, right? ZK is essentially a PhD on top of a PhD in mathematics. It's really complex math, and for many years there's this small group of us math nerds that really love ZK, but no one really paid attention to it until ZK EVM, the meme of ZK EVM. Now everyone's talking ZK, ZK this, ZK that, and no one really knows how it works, right? And part of the problem is like, now you come ask us, what is a ZK, right? We'll start talking about polynomial commitments, Frye-based recursion, folding schemes. You can just see people's eyes glaze over and lose focus. Or maybe you start doing some research into ZK and you bump into some talks by Ariel, like Hassan's theorem. He kind of forgets that people don't have PhDs in mathematics, so it's kind of hard to get caught up. Or maybe you just follow some shitty YouTuber that says, you can make money in ZK. Please don't sue me, BitBoy. So why should you care? It's a new field of math. Like, man, that's cool. Like, and you might say to me, like, I like math, but who studies it for fun? Or you might just say, fuck math. I don't want to learn that. They're really cool. I swear. Just hold on. Maybe I'll get you a bit more excited. It's completely outside of the blockchain too. It's really exciting math. So Vitalik said recently on a Bankless episode that he thinks ZK is as big as blockchain, the invention of blockchain. I actually disagree with him. It's a new field of math. It's a lot bigger than than blockchains. Yeah, I said it. I disagree with Vitalik. What, bro? Come at me. So just to get you like introduction into why this is a big idea is, in the beginning, when we invented algebra, a couple thousand years ago, what we know as modern algebra, there were some farmers that thought, great, I can farm a little bit more efficiently. Or, cool, I can calculate the largest common denominator of a square to figure out what size tiles there should be inside. But thousands of years later, algebra is in everything we do, right? We couldn't have modern manufacturing. We couldn't have the internet. We couldn't have rockets. Even architecture is entirely reliant on these fields of math. So proofs have actually been around for a long time. But previously, to make a proof, every single proof that you were trying to prove, it required you to make this massive book of math to prove that this theorem works, right? Around 2016 to 2018, we made the first form of a non-interactive, generalizable ZK proof, right? So it's a completely new field. It's a new field of math. Like, when were you last around when they invented a new field of math? That's fucking cool. And today we're the farmers. So we think, great, we can make Ethereum a bit faster. Great, we can log into a website without a password. But thousands of years from now, people will be talking about the moment that we invented non-interactive generalized ZK proofs. So what is a ZK proof? And so the sort of current paradigm, the world that we live in, have always lived in, is for any like accounting, for any computation, you had to show every single item and recalculate the whole thing. So you had to list in a receipt that a cucumber is 15 cents and ice is 110, and in the end you get to the total, right? With ZK, it's a new paradigm. Essentially, you can indisputably prove that $15.25 is the result without showing any of the items, right? And it's a new field of cryptography where essentially you, the prover, can prove a statement is true to someone else, the verifier, without giving them any more information than that. So how do they actually work? And here's some examples. The sort of typical example is, Where's Waldo? It's this old French book where you try to find this silly looking guy in between there. And this is sort of the classic example for ZK proofs of, let's say you wanted to prove to your friend you found where Waldo is, but you don't want to show him where. How do you do this? Try to find Waldo for a moment. He's there. It took me a really long time to find him for this example. I sat there for like a half an hour being like, you little Okay, so what you can do as the approver to your friend is you can cut out the picture of Waldo, and then you can send it to your friend, the verifier, and they can check, okay, you found Waldo. But even though this is the classic example, I actually don't really like it because it gets confusing. Like, how do you do this? Like, if you cut it out, then it's easier to find. So a better example is honestly Sudoku, right? And the reason why is actually Plunkish-based systems use kind of like a Sudoku table underneath. So it's the most sort of accurate random example we can give. And so let's say you're playing Sudoku with your friend. You're both doing the same puzzle. Again, you want to prove to your friend, I finished it, but you don't want to show him the result because that guy has to do it on his own, right? So how do you do this? Essentially, what you can do is you take every single row and column, you cut them apart, you put them in a list, maybe you even shuffle around the numbers a little bit. Then you flip them upside down, and that's what you send to your friend, the verifier, right? And the verifier can sort of randomly start flipping rows and be like, okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, all the numbers are there, and like he played it correctly. And this actually becomes probabilistic. The friend doesn't need to flip every single row to be able to essentially, for a fact, know that you did it right, but it works as an example. So you might say, okay, great, but how do I actually create a ZK proof, right? And this is something my girlfriend said while making this presentation. It's like, shit, I actually forgot to explain that. It's a bit hard to explain, honestly, like, because then we get into the math, right? And the way that, like, a simple analogy that you can think of is it might be hard to understand how computers work with zeros and ones, but essentially you have zeros and ones going through logic gates. The logic gates are on a circuit, and a pretty picture appears on computer, right? ZK proofs are kind of like a virtual circuit board. It's not actually zeros and ones, that's to simplify it, but we essentially have some values, they go through logic gates, those logic gates are on a circuit, a virtual circuit, and then you can create the proof. And we can zoom into the proof a bit more. So let's say you want to prove to someone that your passport isn't expired, but you don't want to give them, for example, your passport number because that's sensitive data. So what you can do is you can hide all the other values in your passport, your digital passport. And then what you send is actually the public inputs of when it was issued, when it expires, and maybe your name. And then all of that together, plus you do some calculations on it, is what's called the witness data. And this is what you essentially do. So you take the private inputs, the public inputs, you create a ZK proof off of them, you send that to the verifier. Part of what you send is also that relational circuit. And then the verifier can verify with true or false, yes, this is a valid proof, they really have a passport that has not expired yet. But if that doesn't make sense to you, that's okay, right? Because my hope is that, like, back in the day when we had operating systems on a computer, like Mac or Windows, before we had those, you had to program a custom operating system for literally every single computer architecture. Different CPU, new operating system. And then Microsoft invented DOS, right? And that's a generalized operating system that works like hardware agnostically. And my hope is that with ZK, using like Circum or Noir or ZK EVM, you as a developer don't actually need to know the math, right? You can just write statements that can be provably true, and you don't really need to go into the math. So, like, if you want to go in the math, cool, like, come in, but you don't really need to. You can still start writing programs on top of it. So this is a question I get often, so I put it in, Stark versus Snark. For most of you, it doesn't really matter, honestly. Just a simple version is Snarks are faster and cheaper to verify, which is good because you can stick them on a blockchain and they're cheaper. Starks are more secure, though. They're actually quantum resistant, but they're a bit more expensive to verify. They're more expensive to prove, but expensive to verify. Starkware uses Starks. There's a couple other protocols as well. Snarks are used by most other companies because it's cheaper, again, to verify. So here's some applications for ZK and how it'll actually change the future. So the first and most important thing that you really need to know about ZK is its verifiable computation, right? And this is an example of this, right? So the way that a current blockchain works is we don't have a source of truth, right? So you need a lot of computers that every one of them do exactly the same work, and then they come to a consensus on what is the true state of this blockchain. And essentially, let's say you have a network where there's 3,000 nodes, and you're doing a block. Each block takes 5 seconds to compute. That means around the world, there's computers wasting essentially 4 hours re-executing the same bit over and over and over again. That's just wasteful, honestly, but it's how we get the source of truth. So with ZK, like, again, it's verifiable computation. So you do it once, no one else has to do the work. They can just verify that you did it correctly really quickly. It just gives a yes or no. And with this, we could essentially create Bitcoin with, instead of 16,000 nodes, we could create it with one prover and everyone else verifies it, right? One node, only one full node around the world. We don't have to play this electricity burning game that we do. Like, ideally, you want more than one prover, so you can't be essentially, it's really more of a liveness and censorship issue than it is about being able to lie. But maybe you have 100 of those, and then everyone else doesn't have to re-execute the work. And so the most sort of known use case of ZK is for scaling a blockchain, right? And here's kind of simply put where like each of these little blue things is another transaction coming into the block, right? And the nodes scale linearly. So you get 2 transactions, it's twice as much work. You get 3, it's that much more, right? But the problem is in Bitcoin and Ethereum, we want like a normal computer to be able to participate in this network, right? Like a MacBook. So what we do is we essentially impose a block limit. How many transactions, how much really byte computation can be done in one block so that MacBooks or some cheap nodes could do it. With ZK, it's the paradigm's a bit different, right? You still have like that one big node. In fact, it's an even bigger node than a normal node because that line is not entirely to scale. But essentially that prover scales quasi-linear. So the more transactions come in, the more work the prover needs to do. But every other node on the network just verifies it, right? So we can stick much more transactions into a single block. And that difference between verification and proving is essentially the scalability factor that we can give with ZK to blockchains. And honestly, for Ethereum to become, we hope, the network, like the internet of value, right? We really need more transactions than Visa, because Visa does not do any of these complicated things. We need more than 20 to 60,000 transactions per second, which is what Visa does. So here's an example of scaling. Right now with one ZK L2, essentially you get 15 to 30 transactions per second, right? And with this one single ZK L2, you get another 10 to 100x more when we optimize these a bit more. Right now it's about a double factor, but we can optimize these to about 10 to 100x scalability. That gives us 300 to 3,000, right? After we get proto-dank sharding, which is the new Ethereum data availability layer, you'll get another 10 to 100x cost reduction, or so meaning we can insert more transactions per block, right? After full dank sharding, it's also another 10 to 100x, right? So this is for one ZK L2. We also have Arbitrum and Optimism, and we have all these other L2s coming out. And we already have, at this point, we have, if you get these things together, we have more than 60,000 transactions per second. Like, this is simplified a bit, but essentially when we, a couple years from now, soon TM, we'll have more than Visa, right? And with fractal scaling, like ZKL3s using Validiums, or just doing like a common bridge L2s, we get more and more scaling, way more than we have currently, essentially. And the important thing to note about this is actually sustainable scaling, unlike some blockchains. And part of it is like, this is a one of n security assumption. So you literally need one honest node, and even if all the nodes go down, they can't fake anything, right? Even if every node goes down and it's big and maybe US seizes that data center, the blockchain stops, but no one can steal your money, right? And with some other tricks like data and transaction compression, like proving is parallel. So when we optimize for that, we can get it cheaper and cheaper. I do have a speech coming out in StarkNet CC called Scaling ETH Infinitely. There's supposed to be quotes around infinite. It didn't fit in this slide, so. Essentially, how to scale ETH using shared sequencers, and how do we essentially prevent user experience and like liquidity fragmentation. Interoperability is another use case for ZK, right? So ZK light client bridges or ZK bridges or proof of storage, whatever you want to call it, are essentially a slightly better version of cross-chain bridges, right? Because you have minimal trust assumptions outside of the consensus of the two layers. That being said, it's still a majority trust assumption because you need to verify the attestations of a network. So you need to verify that when you submit ETH state to Solana, that this is actually the real Ethereum state and someone didn't just fork it or make a shadow copy. So it's still not great. Also ZK hyperbridges. So if you have a common bridge like ZK sync with all the L3s, essentially you don't really do bridging between the different fractals. It's just like magic accounting. You just teleport the funds from one ZK L3 to another one. And I talk a lot more about shared sequencers and hyperbridges in the Scaling ETH Infinitely, so we won't go much into details on this. You also get something either asynchronous atomic composability, or with shared sequencers in a common bridge, you also get kind of a synchronous composability. This slide I won't go into because technically this is a 35-minute speech that I'm shoving into 25 minutes. But again, the shared sequencer that's scaling ETH infinitely has much more on this. This is also for bridging in the ZK bridges. I do have a speech from ETH Denver on the next generation of safer cross-chain bridges and why old bridges still suck. Identity is another use case for ZK. So every single application that we sign up with, or website or Uber, we share them all kinds of sensitive data. And it's really quite obnoxious because if any one of them gets hacked or just chooses to sell your data, you're compromised forever. You can't remove your identity from yourself. There's no way to reset that. So one time you get hacked or they get hacked, and maybe your passport data's out there. Maybe for Americans, your social security number is out there, and then you're like, that's my identity. Like someone can be me with that. And so currently, for example, let's say you wanted to prove to someone you're over 18, right? You have to send them the information of this user is 32, right? And if they leak it or someone steals the information from the website's database, they know you're 32, right? With ZK, you can essentially just make a proof saying this user is over 18, right? And the website will store this user is over 18, but you could be 100, you could be 50, you could be 30. It's much less useful information about you to target advertising for or just do something malicious with. Also, let's say you want to prove you're from a country. Right now, you have to say, I'm a Finnish citizen. With ZK, you can just prove you're not from a sanctioned country. There's a lot of countries, again, less useful information for being hacked. Right? Or let's say you want to go to a Bored Ape party and you're a holder of the token. Right? Right now you say which Bored Ape you have, which means they can find your wallet, see all of your finances, right? With ZK, you can just prove you have a Bored Ape without revealing the address. And this is like all of the sort of identity pieces. This is a good example for it of like, when we sign up for Coinbase or Binance or Chase, or maybe if we could legally withdraw money from Tornado, we would have to send them our tax statements, our passports, our like literally everything. And if any one of them gets hacked, you're fucked. If they sell, you're fucked, right? So with ZK, maybe your bank or your government could make an attestation that this person's a real person. They're not sanctioned. They have enough money to sell or like to transfer money to Coinbase, and then you could just send that proof to every single service that you sign up with. Privacy is a cool use case of ZK. One thing to note is most ZK protocols are not private, right? We use privacy for the verifiable computation. You don't need to re-give that information, but there is, like, you can actually hide the inputs, so you can use ZK for privacy, and I hope people do, right? We won't go into this one as much. Same thing with websites. If you log in, a lot of us use the same exact password for every one of those, the same email. One of the website gets hacked. they got literally every single one of your accounts. And again, I won't go much into this. Right now, you have to send them your password. They store your password. With ZK, you could kind of create a proof of, you know, the email address and the password, and they verify the proof, right? Or you could have a private blockchain. An example of this was, until they discontinued it for the next version, is Aztec ZK Money, right? And a privacy protocol essentially allows you to send money to friends or whoever without actually showing your address or maybe the amounts that you're sending. And there are other ways of creating a private blockchain, like fully homomorphic encryption or Intel SGX or MPC. But at the moment, ZK is better. And even in the future, maybe a ZK FHE protocol is really the best privacy solution. And again, so just example of this right now, you make a transaction, you send it to this network, it shows your address, your amounts, where you're sending it to. And again, because we need to reach consensus in this blockchain, every single one of those nodes sees that information and it's widely distributed, as well as the RPCs you're using. With a private blockchain, you essentially make a proof on your local computer showing that you have the funds, that you can make this transaction, and you send the proof to the network, and the network does not actually execute the transaction at all. They just verify the proof. That's the role of the nodes in a truly ZK protocol. Do have a speech on privacy and Web3. Why should you care, and how do we improve privacy protocols to prevent malicious users and hackers? Because I want privacy protocols, but I'm not ignorant of the fact that they would be used for malicious purposes. So, and the last sort of point about ZK is like, just for understanding our world, right? Every time we invent a new field of mathematics, there's massive breakthroughs that we get over thousands of years for that. And like today, we couldn't even make a pencil without knowing algebra, chemistry, and physics. Like the rubber is a really complex chemical structure engineered in labs over hundreds of years. Same thing with the wood, the way they cut it. And the point is, like, ZK proofs don't just apply to Web3, right? We could, like, in this modern day where we can create, like, for example, deep fakes of a Trump grabbing something else, maybe with a trusted element on a camera and ZK, you could essentially take a picture, prove where you took it, that it was a real photo, and then even if you make it smaller or put like a black and white setting on it, they can still tell it's actually the original photo and you really did take that photo and it's not been edited. Or there's some proofs of storage with clouds, or maybe for making normal computers faster, you could have some sort of cache layer where the CPU or GPU would never need to re-execute something they've executed better or before. For machine learning, maybe Google could use third-party providers instead of building these massive data centers to actually train their machine learning models, and they wouldn't have to trust the third party actually ran the machine learning model instead of sending them some random information. And like there's a paper actually on how cryptography might help us understand actually black holes more than just like normal physics. Like ZK might actually help explain some of these concepts like quantum entanglement. And I've actually talked to some physicists about this, or quantum physicists. There is certain properties like quantum key distribution that ZK proofs might actually help us explain quantum physics, parts of quantum physics. The point of this speech is math is cool. Just kidding. Like whether you care about math or not, or ZK or not, you should pay attention because it's going to change the world around us. Thanks for caring, and hopefully you didn't get overwhelmed with math, because there was none. And you can follow me at ZK Lumi on Twitter.
Yep. Questions?
So the question was, a lot of people confuse ZK with privacy, and sort of what is the difference of just using zero knowledge for scaling versus actually privacy or some other application. And the idea is like, again, you don't need to rerun the execution. So you don't need like which transactions came into the blockchain, for example. And that's how you get privacy. But the reality is like ZK Sync or these other ZK protocols, they still send to explorers your address and every single transaction. And this helps essentially you keep taxes or go to Etherscan and actually see your transactions, right? So they choose to provide the data so that people can see it, so it's a public network. But because it's verifiable computation, you could literally just throw away all that data instead of providing it to explorers, or you could make it so only the person that made the transaction can actually see what transactions they did. So it's a choice to use privacy or not, right?
So recently ZK got a lot of traction after following blockchains, right? But it exists long before blockchains. Is it because blockchain or money is the biggest use case, or why world was not paying attention to ZK before?
So math and cryptography typically don't really get any funding, right? There's some random universities that do it, and maybe government gives something. The reason why ZK is moving as fast as it is, it's shocking how fast it's moving, is because it's tied to actual money. So if you develop some of these primitives, we can make blockchains more scalable or actually provide privacy. So it's the perfect funding mechanism for any cryptographic protocol that we use. And actually ZK, the Ali Ben assassin, his first use of ZK was for Zcash, right? So it accelerated the funding behind the actual math itself, which is great, fun math.
Yeah, I was just wondering, you've mentioned there are so many use cases even outside of Web3, right? So my question here is what do you think about the adoption? Like, what are the incentives for other parties? We still live in a world where most of the business models are based on monetizing the data and all this kind. Won't there be kind of a pushback? Backfire, like I'm a user, right? So I care about my data. I want this, but is it just I can make that decision and implement ZK proofs, right? Or it has to be kind of a consensus, like an agreement on the other side, and maybe they have completely different incentives. So what do you think? Like how do you see the adoption happening in the next few years?
Yeah, so again, it's an incentive question of like, Twitter could create ZK proofs to show that they really ran the algorithm that they now open sourced, instead of just open sourcing it and saying, trust me, bro, we're running this algorithm. There's just not a lot of incentives right now. So if the community, like just normal people, start demanding this with machine learning getting smarter and scarier for people, maybe they'll actually start doing that. Like if Google runs out of capacity one day, needs to train more and more and more data, maybe they'll start using ZK proofs because they don't want to have to trust. So it's all incentive models. And luckily, we're building out such great tooling and libraries that today to make a Circum program does not take long. You can do it in a couple of days for even complex applications. So that'll make the adaptation easier instead of 4 years ago, Google having to hire like a team of 50 engineers working their asses off on it.